So that is the basically introduction of the concept. And right now, again, this section will be kind of the qualitative, and that is about the classifications. And in these sections, along with the going over the kind of the definitions, then I'm going to gradually define the scope of the learning in ME 408. So kind of give you some kind of expectation of what kind of the topic I will show you. Okay. So the first difference, the first category is we have the discrete versus continuous systems. And the discrete system is such that we approximate a continuum into a summation of a collection of the lump mass. Okay. And so this one, formulation is can be formulated in terms of the ordinary differential equations, and compared to if we're going to study the continuum, and this one we can do it, and this one will based upon a lot of information on the ES 331 mechanical material, and we can do it. Okay. And actually, if you remember in chapter 9 of the mechanical material and diffraction of beam, there we have a little bit taste about the partial differential equation, but somehow we can step away very quickly. We can start from there. And basically, this kind of continuous system will lead into the differential equations, the partial differential equations. So in this semesters, we won't touch these. We will deal with discrete. Okay, so that is our topic. And the second one is the undamped with damped vibrations, and that we've been talking about. So this is without damping components. Here we have damped components. So we're going to we're going to expose ourselves to both of the systems. And the solution process is the same, but due to additional components like the damping, that will make a little bit more more complicated description of the system vibrations. Okay, so that is the one here. And for the damping, basically here we consider is the damping is from frictions. Friction have different type. We have the viscous friction, so basically that's the viscous damping. And we have a dry friction. The dry friction basically the coolant frictions. And we have more, and in this class, I'm going to only focus on the viscous damping, okay, and other nonlinear damping components I won't touch, okay, and that should be the next. Sorry, let me skip this page a little bit more. I'll be back. So another is linear versus nonlinear vibrations. Linear, that means once we formulate the formulations and the mathematical description, that equation is a linear equation. So that means we're going to deal with only the linear differential equations, linear ordinary differential equations. Everything nonlinear, we won't touch it. Okay. Basically, my goal is we go over the most fundamental and the common terms in linear vibration systems. Okay, so that means back to our the damped frequencies here. The frequency on the friction, the coolant friction, which is on nonlinear term, we won't touch it. Okay. For free versus forced vibrations, free vibration is such that, for example, I make an example here. So, for example, here I drag the mass block to here and release it. Once I release it, the system is going to oscillate on its own without any existence of externally loading. Without any externally loading, during the vibration process, we call we call it as a free vibration. Free, that means free of any externally existent loading. Okay. Forced vibration is such that, say, I use a robot arm. The robot arm is kind of always been attached to this mass, and and the robot is always doing the influence. He's applying his influence over the vibration history. So that is the existence of the externally applied loading always there during the vibration. So we call this called the forced vibrations. And in terms of the free vibrations, we're going to only deal with is to find the features of the vibrating system, for example, the natural frequencies. The natural frequencies, again, that is the intrinsic features of the system once the spring and mass is determined. The forced vibrations, in addition to the natural frequencies of the system itself, we also deal with the working frequency. The working frequency can be the frequency that is applied through the loading. So this frequency, this system will become very complicated because we're going to deal with both things, dealing with the intrinsic properties as well as the loading applied. So in terms of mathematics, we're going to solve for this system is corresponding to we call the non-homogeneous differential equations. That is the formulation here. So if you have something in your memory, you better to begin to review your lecture notes before, okay? And so that is a topic we are going to going over. Okay, we're back to a little bit linear nonlinear systems. Again, a linear system is that the formulation will be linear, and linear system, that means superposition principle can be applied. Okay, so keep this in mind. So that is a good way we talk about the linear system. Nonlinear systems that can arise from, for example, the existence of the Coulomb frictions, the existence of any nonlinear term from the damping. And damping, later we have a little bit more discussions, but from your mechanics of fluid, the fluid mechanics, you know many times the fluid behavior actually can be nonlinear. Okay, so that is the term where the damping, nonlinear damping coming from. And again, we don't touch any nonlinear terms from frictions, from damping. So that is the one here, okay? The last classification is we call the deterministic and versus random. And deterministic signal, that means something like this. And basically that has a well-defined behavior. Either that is periodic, showing here is a periodic functions, or that is imperiodic. That means there's an arbitrary function, but that is the well-defined in the, say, time domain. The random excitation or the random force application is such that, for example, if you, I don't know whether you learned from fluid mechanics the turbulence. Probably not, right? Basically the random, that means you have to involve with the, let me make one example using the random, the normal distributions. So that means you're going to describe this kind of function with average and the probability of the numbers away from the average. So that means you're going to this function includes two terms. One is average, one is 3 sigma. Sigma is the standard deviations. Okay, so usually they describe such a function is, say, something like this. Say xt, the average, and plus minus, and the 3 sigma. Okay, 3 sigma is the standard average. So every single parameter will have the similar form, and sometimes they're using the kind of the notation for something. Okay, so but this one belonging to is more advanced topics, and again, in this semester we only deal with the deterministic, and no probability theory will be kicking. Okay, that is this, and